Buffers. Buffers are solutions that resist pH change, and we're going to play around with buffers in lab today. What makes a buffer is something that has significant amounts of both a weak acid and its conjugate base. So what happens is, if you've got the weak acid and the conjugate base, they're in equilibrium, you have significant amounts of both of them. If you get base that's added to that, the weak acid will react with it and neutralize it. If you add acid to that solution, the conjugate base will neutralize it because you have both acid and base present. So whether you add base or acid, there's something to neutralize it. A buffer cannot absorb an infinite amount of acid that's added, but it can absorb a significant amount. Your blood, your blood, because you are all human, except for the vampire in the back, right? Human blood is a buffer. Your blood has a pretty sophisticated buffering system in it. And in a healthy individual, your blood pH is between 7.36 and 7.40. And if it drops below 7 or gets above 7.8, you will die. That would be bad, right? Because the pH in your body affects a lot of different reactions. Your body is a biochemical factory. Reactions like you would just not even believe. It's really cool to get into them and study them, but not in this class. So let's look at this. Here's an acetic acid sodium acetate buffer. So this is acetic acid. That's a weak acid. It's not on that list of strong acids. If we add sodium hydroxide to this, the acetic acid neutralizes it and forms sodium acetate, the conjugate base. If we add HCl, the conjugate base that's present neutralizes that, forming the weak acid. And so no matter what you add, it can neutralize it. Pictures are better. Okay, so here we have a beaker, and this is the acetic acid, and this is the conjugate base. So maybe let's write an equation for that, because that might be helpful. So acetic acid, HC2H3O2, in water. It's a weak acid, so it's in equilibrium. It forms H3O plus and C2H3O2 minus. This is the acid. This is the conjugate base. So here we have the conjugate base and the acid, and they are both present. So when we add hydrogen ions to this, the hydrogen ion can react with the conjugate base, forming some more of the acid. If we add hydroxide to it, the hydroxide will react with the weak acid and form some of the conjugate base. The pH will not change significantly. And you're going to look at that in lab today. We've got pH meters, and you're going to take solutions that are buffers and solutions that are not buffers, and you're going to add acid and base to them and see what happens to the pH. And you'll see that things that are not buffer solutions, you add a drop or two of a strong acid or a base, and the pH will change significantly. But with a buffered solution, you can add many drops, and the pH will really not change at all. It was kind of cool. So what do you need to know about buffers? You need to be able to recognize what is a buffer solution. So a question like this: which of the following is a buffer solution? And to do this, we have to be able to recognize conjugate acids and bases. So H2SO4 and H2SO3, is that a buffer solution? Is one of these the conjugate acid and the other the conjugate base? No. Remember, a conjugate acid and base differ by one hydrogen ion. So we're looking for a difference of one hydrogen ion. This one has 4 oxygens, that one has 3 oxygens. There's something different, so that's not. How about HF and sodium fluoride? This is an ionic compound, right? We're told here that it's soluble. So what does that form? Sodium ion and fluoride ion. This is the guy we're looking at. Is this the conjugate base of that acid? Yes, it is. Because if we remove H plus from this, what do we get? F minus. So HF and F minus, this is the acid, this is the conjugate base. Well, why don't they just list F minus in here? Well, because you can't have a solution of just ions. There's got to be some sort of a spectator ion, another cation in there to be with the fluoride. So this, one more question we have to ask ourselves. Now this is the acid. Is it a weak acid or a strong acid? That's a weak acid. So this one is a buffer solution. If it's a strong acid, it will not be a buffer solution. So let's look at the next one, HCl and sodium chloride. Well, sodium chloride forms sodium ions and chloride ions. So that chloride ion is the conjugate base of this acid, right? So we're looking good so far. But is HCl a strong acid or a weak acid? It's a strong acid. So even though we have a conjugate acid-base pair, it's not a buffer because it's a strong acid. The strong acid dissociates completely. And so there is no intact acid left to react with a base. And so that's just not going to work.
Okay.
Yes?
Can you just do a quick summary of how you know a strong from a weak acid?
Strong acids are on the list. How's that? There's a table in your book. There's 6 of them. Yeah, that's all there is. There's no magic system. That's it. How about these guys, sodium chloride and sodium hydroxide? Is that a buffer system? No. They both have sodium, but we don't have an acid and a conjugate base, right? Hydroxide ion, we say, well, that's a base, but what is the conjugate acid? It would be H2O. We don't have a weak acid conjugate base. Okay, so that's the only one. So you're looking for a weak acid. So letter C here, we see HCl. If we identify that immediately as a strong acid, we can say, that one's not a buffer, without even looking any further. But what we're looking for is that it's a weak acid and that you also have the conjugate base. And that's how you identify those. And there's chapter in review. Woohoo!